morning, everyone. Today we will be speaking about the EMBARK wastewater deep tunnel conveyance system. My name is Nadia Rendon.
I'm Stephanie Thompson.
I'm Anna Close.
This is a multifaceted transit revitalization project that will be taking place along the 7.5-mile segment on Route 1 in southern area of Fairfax County, Virginia. The purpose of this project is to expand the highway to 6 lanes from its current 4 lanes, as well as there will be a wide median to accommodate a future planned bus rapid transit system. And along this Route 1 project, there will be 7 mixed-use developments coming in. And so because of that, there will be activity centers, business centers, bringing in a lot of population, because people will be coming to these developments that this area is not accustomed to, that will be projecting a higher sewer flow. A little background on this area: the development that started in this area began back when George Washington was a homeowner in this area, and it was further developed without any coordination with the local infrastructure. And so the existing system, it works well for its current conditions in the area. However, it is not going to be sufficient enough to handle the future projected flow. The existing collection system, this project will be taking place in it's completely contained in the Accutank Basin, which consists of 375 miles of sewer lines. And those sewer lines are made up of 3 predominant types of pipe material, which include asbestos cement, reinforced concrete, as well as polyvinyl chloride, which make up 90% of the basin's pipe material.
So when it comes to planning, projections, and modeling, for the existing planning documents, we emphasize focus on utilizing the EMBARK final comprehensive plan provided by Fairfax County. This shows all of the developments along Route 1, all the different community centers and employment centers that they're going to really focus on the development around. The existing data that we utilized included the Fairfax GIS data. This was necessary to really evaluate the different sewer and wastewater, different pipelines, and then the MCOG, or the Washington Council of Governments 9.1 version of the Transportation Analysis Zone data. This was necessary in order to evaluate the different population and employments from 2015 to 2045. The Fairfax County provided us Accutank pump station fluorometer data from 2012 to 2017. We looked at this to determine what the average flow was for historical components. So we averaged a 5-year of 10 MGD, or million gallons per day, and there was a peak flow exhibited at 24 MGD, and the design capacity of the Accutank pump station is at 37 MGD. So our unit flow factors were obtained from the PFM, or the Fairfax County Public Facility Manual, and this broke up how we contribute different flows towards populations and employment. And from this, we broke up the TAS data as well, based on the different regions from 2015 to 2045. And we averaged the future flow for 2045 to be 14 MGD, with an expected peak flow of 47 MGD. So our modeling approach, we looked at a few different softwares, and we decided that the EPA stormwater management model was the best for us. It's free, it's easy to use, and it's got a really helpful tutorial to work with. So through this, we also did a data verification process where we analyzed the different sewers and how they lined up, if there were any major breaks in them. And we kind of collected and compiled that into the EPA SWIM. Then from this, we looked at the existing flows and the future flows. From our data basis, or the data and basis of hydraulic modeling, we looked at all of the GIS pipes in this region, or the Accounting Pump Station service area, and this accumulated to 10,872 pipes. We broke this down, because that's a lot of pipes to work with, to a representative model of anything larger than 15 inches. And this came up to a representative skeleton of 171 pipes. When we looked at incorporating all 171 pipes into our model, we also looked at kind of we incorporated our wastewater flows that we had calculated, and we brought that into input nodes from where we had cut off along the pipe network. And we looked at the existing and future projections that we had brought in from the TAS data. When it came to model calibrations, we looked at the pipe slopes, making sure that the elevations were there, and we also looked at the existing flows and the existing flows from the Accounting Pump Station flow meter data, and we did like a plus minus 5% to kind of calibrate that compared to what we project. And we ended up with a maximum depth of flow over the depth of the diameter of the pipe of 80%. So that's what we associated for what would be considered at risk for an SSO or sanitary sewer overflow. And we determined that 140 pipes will be over capacity by 2045.
I'll be talking about alternative screenings and decision matrix. Based on our models, we came up with 6 possible alternative solutions that would remediate the overcapacity of the issue. The first alternative was to increase the capacity in the current location. Therefore, we'd just be adding a bigger pipe diameter in the current location. The advantage of that would be to stay within the VDOT right away, and it also would help during constructions to be concurrent with the Route 1 widening. However, on the pipes are composed of 30% asbestos, and with environmental issues will require special considerations with disposal and thus driving the cost of the project even further. Due to the cut and cover method, MOT will require lane closures, therefore would negatively impact the traffic in the region. Alternative number 2 will be to install a small parallel gravity sewer system next to it and cure the existing pipe with cured in place pipe method. This alternative will have the same advantage as alternative number 1, however, it will avoid the bypass, and therefore bypass failure can cause more traffic in the region. This method will also not accommodate for disturbance of the traffic, and due to the boiler truck required by the CIPP method, the overnight usage would create a lot of noise and odor, and thus disturbing the community. For alternative 3, we looked at rehabilitation using trench techniques. We looked at pipe bursting and sectional slip lining. However, when consulting with Fairfax engineers, we found out that the Department of Public Works and Environmental Service, they rejected this alternative. And they were heavily because the asbestos contained in the pipe, and also there are other situations where the pipe bursting can get stuck and other issues can create. Our 4th alternative was to create an offline retention basin. This would just capture the peak flow, and during last flows, they could be released back into the system, and this alternative was also rejected by the DPWS since it is very expensive due to furniture costs, maintenance, electrical, and chemical expense. Also, this facility produces a lot of odor, and therefore, since this would be in a community heavily populated, it would create another big issue regarding the community impact. Furthermore, this location will require a lot of permitting and will take a lot of time to get processed. Alternative 5 would be the new gravity sewer alignment. Advantage because it would be a new line, require low maintenance and operation. But on the other hand, this location has a lot of historical grounds and military grounds. Therefore, permitting would be very difficult and time extensive. Lastly, a sixth alternative would be the tip conveyance tunnel system. And this would create a whole new main sewer collection, storage, and conveyance system. Due to excavation by a tunnel boring machine, will be happening 75 feet below ground. You're not interfering as much with disturbing the community with the dusting, noise. It won't disturb the local business. And this alternative will also bring future developments. We also bring the capacity to accommodate future developments and population growth to the area. This project will require a full geotechnical mapping and alignment insurance. Based on the alternatives, we came out with a multi-attribute decision matrix to come out with the best possible course of action. We developed criteria and weighted them on a scale that show the importance to the solution of the project. As you guys can see, the dip tunnel did show the best possible outcome and is the recommended solution or course of action. It would further accommodate the EMBARK development, future developments, and population growth. It would, since it's being dug underneath the ground, would bring less amount of disruption to the community and to the local business. And also, it would help with constructability and the time of the project delivery. And we also found this option to be the most effective and less costly maintenance.
So the deep tunnel conveyance system is approximately 6.3 miles long with 4 strategically placed drop shafts. The tunnel itself is 14 feet in diameter, and the inside diameter of the pipe is 10 feet. This image shows the tunnel system with the 4 drop shafts and also the sewer system and the red lines within the Academic Basin. This is the profile view of the tunnel with the 4 drop shafts indicated at the blue and black vertical lines. So a drop shaft will connect the existing gravity sewer to the main tunnel by using a vortex shaft. The top image is a 3D rendition of the drop shaft with an access to the main tunnel. The image below that is the vortex shaft, and a vortex shaft is a way to control the wastewater velocity going into the main tunnel. So we decided to implement an odor control system to reduce odor caused by the wastewater traveling through the main tunnel. This odor control system sucks up the odorous air by using a vent or a fan and sends it through multiple layers of activated carbon, and we decided to implement this due to the construction's proximity to residential areas. We looked at many companies that provided activated carbon in bulk and decided on these 3 companies due to their knowledge of the product and positive feedback. The supervisory control and data acquisition, or SCADA system, will be used to monitor flow levels and water levels through CCTV. This is a list of permits that we are currently looking at. However, during construction and design, the list could change. The one interesting permit, the VPDES permit, states that if over 1 acre of land is disturbed, then we'll have to apply for it, and saying as the staging areas, drop shaft, and gravity sewers are all over 1 acre of land, we will have to apply for it. It also includes the VAR 10, where we have to renew it every 2 years. It's important to keep in mind the timeline of applying for a permit from start to finish, which will be approximately 1 year. This is other considerations that we had to take into account. We really wanted to focus on the public outreach because the construction is close to residential areas. And we want to let the public know about how the construction will affect their day-to-day lives. So we looked at 3 construction procurement methods. The first was the design bid build, the second was design build, and the third was the construction management at risk, or CMAR method. We ended up going with the CMAR method due to the owner's ability to choose the best designer and contractor, and it reduces cost overruns. Now I'll be going over capital improvements and programming. This is a projected timeline. It is approximately 7 years from start to finish, and the reason that it is 7 years is because of the CMAR method, where while designing can be finishing up, we can also start the construction, such as staging areas and getting the tunnel boring machine. We looked at unit rates using the Hatchmont-McDonald forms to get unit cost of certain materials. We also researched bid tabulations, and bid tabulations are a way for the general public and contractors to see unit costs for materials. So as part of our ongoing QA/QC process, we had to revise our initial cost estimate to be around $246 million. We had to revise it due to the tunnel diameter being 14 feet.
So due to the revitalization project causing stress to the existing sanitary sewer system, the implementation of measures to increase capacity will be required. And so after the swim modeling and the decision matrix, the deep tunnel conveyance system was the best course of action because it limits impacts to the affected community and environment, which outweighs the additional technical and monetary costs. And after a preliminary assessment of the required infrastructure improvements, the EMBARK revitalization project will be able to proceed. These are a list of our references, and we want to say thank you to Nikolai Gurdian, who could not present with us, as well as everyone else who helped us get to where we are. And a special thank you to the VWEA judges, committee, and Henrico WRF, as well as Dana Hargrove for organizing this event.
Thank you very much.